Okay, so I'm recording. Okay, good morning everyone. So we're going to start a new topic today, which actually has been kind of motivated by our previous discussion. So this is deadlocks, which is chapter 7 in Galvin's book. So we have briefly come across this term, but let us formally understand it. So deadlock is a situation where a set of processes wait for each other's action indefinitely. So they are blocked because they are waiting for some action by some other process. But then that action can only be taken by another process which is also blocked. Right? So this is a solution with no, like if you let this situation be, there is no cure. All processes in the deadlock will remain blocked permanently. Of course, something can be done. That is what we will discuss over the course. But then if nothing is done, I mean, you just give time, etc., that won't help. So the processes will remain blocked indefinitely. So let us understand first how a deadlock happens. For that, this is the system model that we will consider. So the system consists of a finite set of resources which are to be distributed among a set of competing processes. So competing means competing for the resources. And we assume there can be m types of resources. And resources can be of like these, so the CPU cycles, memory devices, IO devices, and so on. Actually, resources can also be not only these kind of physical devices, but also logical devices. Like we discussed deadlocks in the context of semaphores or mutex locks. So even those can be resources. Like a particular semaphore is controlling, I mean, okay, maybe the resource is not actually waiting for the semaphore, or the resource is not competing, sorry. Possibly the processes are not competing directly for the semaphore. They are competing for some resources. But then those resources can be protected by semaphores, as we have discussed. And each resource type may have several identical instances. So just let's say that Ri, this resource type Ri, has Wi instances. Now, if our process asks for a resource of a particular type Ri, we assume any of the Wi instances of Ri can be allocated to that process. And we also assume that every process is following some rules. So they first request for a resource, maybe to the operating system. Then they use the resource and finally they release the resource. So the OS again comes to know when a process has released a resource. Okay. So that is the system model that we are following. So in this kind of a system model, how can deadlocks occur? Let's say a very simple example. Say a system contains one tape and one printer, and consider these two processes P0 and P1. So in general, nothing wrong with the processes. Like if you look at the processes independently, the codes, etc., all are fine. However, a problem can occur if, say, P0 gets hold of the tape and P1 gets hold of the printer. And let's say there is only one tape and one printer. So then now P0 is requesting for the printer. So it's basically waiting for P1 to release the printer. So P0 is blocked. But P1 is also blocked because it is requesting for the tape. So it will be blocked until and unless P0 releases the tape. Right, so P0 and P1 are waiting indefinitely for each other. And understand that just giving time will not help here because neither P0 nor P1 will actually come out of the blocked state. Okay. Let's take another example of a deadlock. This is similar to what we discussed, I think, yesterday itself. So we discussed this in case of semaphores and processes, but we also know that threads also can be synchronized using mutex locks and semaphores. So here also see these two threads. So let's say we'll create two threads in the process. One thread will execute in this function and another thread will execute in this function. So now if you see the pseudocodes, again that's a very similar situation where say one thread gets hold of first mutex and is waiting for second mutex. another thread gets hold of second mutex and is waiting for first mutex. So a very similar situation like what we had in the previous slide. Okay. So these are just simple examples of deadlock. But now let us formally understand when deadlock can happen and so on. So formally, deadlock can arise if four conditions hold simultaneously. So these are necessary conditions: mutual exclusion, hold and wait, no preemption, and circular wait. So let's understand. The first one is easy. So mutual exclusion means only one process at a time can use a resource. Now some resources are by definition shareable. Say for example, a read-only file. You can let multiple processes read from the file. Like this is the scenario we encountered, say, in the readers writers problem, which we discussed yesterday. If it's a read-only file or there is just a buffer which many processes want to read, you can actually let this resource be shared. But then some other types of resources are by definition non-shareable, say writable file, or maybe you have just one processor, right? Or you have just one printer, so you really can't share it. Second condition is hold and wait. So in this model, we assume that a process continues to hold the resources that are already allocated to it while waiting to acquire additional resources. Okay. Okay, just before going on ahead, this hold and wait, does it immediately tell you something about how, let's say, this situation can be handled? This hold and wait. Does it immediately ring a bell that, okay, then what could be a possible solution to prevent this kind of deadlocks? Exactly what Pankaj said. So if we simply, okay, so what Dhrumil said is also a possibility, but then what I had in mind is what Pankaj and Soumitra was telling. Okay, let me clarify. It's good that I see different options. It's good for multiple reasons, like Friday 9 a.m. class. Yeah, I always get nervous how many people are awake. So this shows at least some people are awake. Good. Okay, but coming back, uh, okay, what Dhrumil and Vij have said, they are also possible mechanisms. Okay, like what Dhrumil said. That's one idea of saying that, I mean, okay, basically the same idea that either get hold of both resources, printer and tape, or don't get hold of anyone. So you can have another semaphore which will lock both the printer and tape together, something like that. Also what Vij said also makes sense, but then specifically with respect to that no hold and wait condition, I had in mind what Pankaj and Soumitra pointed out. Like if we follow this protocol, that suppose P0, it has got hold of the tape. But now when it requests for the printer, the OS tells it printer cannot be allocated. So P0 understands that I have to wait, as in I have to block myself. So in that case, why should I still hold the tape? It's wasteful. Why allow a blocked process to hold a resource? So let's say P0 also releases the tape before blocking itself. That will solve the problem because then P1 will get hold of both. It will complete. Then at some other point P0 will be allocated the processor again, and at that point maybe it will get hold of both tape and printer, right? So see again, I mean, I just wanted to tell this up early because I might have given a false impression that nothing can be done if deadlock happens. It's not that. Just like you have to plan better so that, yeah, I mean, what can be done, right? Okay. Okay, going back. So hold and wait. I hope you understand that why is it necessary for deadlock? Because if there is no hold and wait, possibly there will be no deadlock. Third is no preemption. Okay, I have a question. So Shomitra asks if some critical section between request tape and printer and also some part after releasing printer. Okay, so you are telling some critical section. Okay, let me go back to that slide. So you are saying if some critical section starts between request tape and printer and also some part after releasing printer. Yes, you are right. Sure. Okay, P0. Yeah. Okay. If some critical section between request tape and printer. Okay, so the critical section starts in between these two and also some part after releasing printer. Yeah, I agree. Sure. So if in the critical section you actually require the printer or maybe you require both tape and printer, then this cannot be done. But then see, that is exactly what we are telling. Let's say the protocol is that P0 will not even start the critical section unless it gets hold of both resources. If that is the protocol, then possibly you should not start a critical section at this point where P0 has got hold of the tape but is still requiring the printer. Okay, so if we follow this protocol, then this happens. Of course, the question that you asked is not following the protocol. So if there is no such protocol, then deadlocks can happen, right? But as I'm saying, if we follow that kind of a protocol, some of which we will discuss, then such situations can be avoided. Like basically, you know that suppose the protocol is that if you ask for a resource and you are not being able to, I mean, the OS is not able to allocate it, then you should go block yourself and you should not hold any resource. If this is the protocol that every process will follow, then a process should not start a critical section like this, where it has got hold of a tape, but it has not yet got hold of a printer. Then it should not start a critical section in that scenario. Okay. So again, this is what I'm telling is an if statement. If you follow such protocols, then the problem will be solved. Okay. So we discussed the first two conditions, mutual exclusion and hold and wait. Third necessary condition for deadlock is no preemption. That means a deadlock can only happen if a resource can be released only voluntarily by the process holding it. So again, you see that now the previous hold and wait thing we kind of expressed is as a protocol that the processes themselves follow. That if they have to wait or if they get blocked, they will not hold any resource. The same thing can be achieved by kind of forcibly, that the OS can preempt a resource. So again, going back to the previous slide, suppose P0 has got hold of the tape, but it is not, so it has got hold of the tape. Now it requests for the printer. The OS sees it cannot allocate the printer right now. So the OS also preempts the tape from the process P0. Because now that that process will be blocked, no point in keeping the tape allocated to it. So the kernel forcibly takes away the tape from P0. Of course, both the tape and the printer will be given to P0 when it will be active, but at present it will be blocked. So no point in keeping the tape allocated to it. And the last condition is interesting, the circular wait. So basically there should be a set of processes such that P0 is waiting for say P1, P1 is waiting for P2 and so on. And there is a circular end, that is Pn-1 is waiting for, Pn is waiting for a resource that is held by P0. Right? So there is some kind of a cycle. So as I said, in this set, every process is waiting for another process of the same set. Okay. So all these are 4 necessary conditions for deadlock. If one of these don't hold, deadlock cannot occur. And what we will see later is that actually one technique to deal with deadlocks is to ensure that at least one of these conditions do not hold. Okay. Any questions at this point? Otherwise, I'll proceed. Yeah, it is at these times that I don't understand if anyone is awake. Okay. Hoping you are awake, let's move ahead. Okay, now we will try to characterize deadlocks using a different approach, using a graph-based approach. So here we will study a graph model for resource allocation. So technically the full name of the graph is resource request and allocation graph according to the book Galvin, but then it's for simplicity is just called the resource allocation graph. So let's understand. Whenever we are describing some graph, usually, I mean not only in the OS course but in many other courses, the standard way is to discuss what are the vertices and what are the edges. So there are two types of vertices, process nodes and resource type nodes. So a process node is, I mean, there will be a node for every active process in the system. And these are denoted as circles. The resource type nodes is the set of all resource types in the system. Remember, we are not talking about resources, but resource types. Okay. Of course, there will be a representation of individual instances of each resource type. We will see a picture, then we will understand. And these resource types are denoted as rectangles. Now we will discuss the edges, but before that, just intuitively, let me ask you, can you guess what the edges will be? Remember, we are trying to use this graph to model or to represent how resources are getting allocated. And we have these two types of nodes. So what do you think the edges will be? Waiting processes. No, Soumitra, again, see, processes are nodes. My question was about the edges. Like, so edges don't correspond to processes. Yeah, what Shomnath said or Shubham said. Okay. Okay, yeah. So first of all, the edges are between the processes and the resources, right? Now what Shomnath, okay, what Shubham said is U to V is an edge if resource V is allocated to U, right? That's one type of edge. There is another type of edge. Anyone can guess it? That is also between process and resource. Exactly what Ayush pointed out, request edge. Okay. So request edge. So okay, actually what Ayud, Shomnath, Ayush, yeah, basically Ramnivas, all of you are telling the right thing, like the same thing basically. So basically there are two types of edges, a request edge and an allocation edge. So when a process, the PI, has requested an instance of resource type RJ and is currently waiting for it, then we put a request edge. So this is an edge directed from a process to the resource type. Okay. And the allocation edge is kind of opposite. So suppose a instance of resource type RJ has been allocated to PI, then we put a directed edge from RJ to PI. Okay. So the directionality is reverse, right? Directionality is reverse. Quick question, very intuitively. Why do you think the directionalities of the edges reverse? As in, this is from process to resource and this is from resource to process. Very intuitively, like, why do you think the directions reverse? I mean, why are we not saying that this will also be PI to RJ? Okay, for differentiating the processes added in the edge. Okay, makes sense. Yeah, okay, fine. Yeah, sure. These are one example. I mean, these are some possible reasons which you are giving. Like we want to distinguish between two edges. I mean, two types of edges. One is a request edge and an allocation edge. See, understand that this graph is changing with time, right? So there should be a representation of when a process is waiting for a resource and when a resource has been allocated to the process. Okay? So see, both these edges are between Pi and Rj. So if you completely keep them the same, there will be no way to distinguish whether Pi is waiting for Rj or whether Pi has already got Rj. So that's definitely one reason, right? There is another small reason which will be evident as we go ahead. So wait for it. Okay, so Radhika, okay, let me just clarify this point. First, it's an important point. So first of all, understand that the RJ that we are mentioning here is not a resource, rather it's a resource type. Okay. And whether a resource type has only one instance or multiple, that depends on the system. So a particular resource type can have just one instance, can have many instances. But I understand the kind of confusion. Let me show some pictures, then things would be clear. Yes. So this is how the graphs will look like. A process would be a circle. Okay. A resource type with 4 instances is actually represented like this. It's a big rectangle with 4 small rectangles. So now when Pi requests for an instance of Rj, we put this kind of an edge. Because Pi is basically happy if any of the instances of Rj is allocated to it. So Pi is just requesting any instance of resource type Rj. But when a specific instance of Rj is allocated to Pi, then we actually indicate, first of all, the direction of the arrow changes, and we specifically indicate that which instance of Rj is allocated to Pi. Okay. So one resource can be allocated to only one process at a time, right? But a resource type can have more than one instance of the resource. Okay, what Pankaj said, yes, there are other possible ways of distinguishing between a request edge and an allocation edge. You are right. Then here the directionality has been changed. That's also one way. But as I said, there is another reason which will possibly be evident in the next 3 or 4 slides. So wait for it. Okay, so any questions till now? Is the resource allocation graph clear? So let's say here is a resource allocation graph. So P1 is waiting for a resource type R1, P2 is waiting for a resource type or resource of type R3 and so on. And let's say for R2 there are these two instances. One is allocated to P2, one is allocated to P1 at this point of time and so on. Okay, so this is how a resource allocation graph look like. Any question at this point? Because the next few slides will require that you have understood the resource allocation graph. Okay, good. Then a quick question. Pankaj has a brilliant guess. Yes. So let's wait for it. So good guess, Pankaj. That's a excellent guess. Yeah. So just wait for it. So yeah. So the thing is, now this resource allocation graph will change with time. Okay. How will it change with time? So when Pi requests an instance of resource type Rj, a request edge Pi to Rj will be inserted. When the request is fulfilled, that means actually an instance of Rj is allocated to Pi. The edge is changed to an allocation edge. And when PI will finally release this resource, the allocation edge will be deleted. Fine. This is how the graph will change with time. Okay. Now comes this thing. So we have defined a graph. Now let's join like how does this graph help in understanding deadlocks? So this is the resource allocation graph with a deadlock. And so here I intended to ask the question that why do you think there is a deadlock here? But Pankaj has already given the answer. So there is a deadlock here because there is a cycle. Okay. And yeah, another small reason why we changed the directionality of the edges between weighting and allocation is that we want to take advantage of the fact that if we do so, then a cycle will a cycle will indicate a deadlock. I mean, if we did not change the directionality of the edges, then we would not have got a cycle. Okay. But now convince yourself that, okay, so let me ask Pankaj. So Pankaj, explain, why does this graph show a deadlock? You can unmute yourself and tell.
Hello.
Yeah.
Yes, sir. So the four conditions that we mentioned initially are all satisfied.
No.
The cycle is especially pointing to the fourth condition, where one P1 has resource.
Explain in some more detail, as in explain in terms of P1, P2, P3, like why is there a deadlock here?
In this particular one.
Yes.
Okay, so P1 is requesting for R1 and has R2, but P2 is requesting for. Okay, let me see on cycle once. Okay, the P2 is requesting for R3, but R3 is allocated to P3, while P3 is requesting for R2 and R2 is allocated to other processes. So neither P2 nor P3 can proceed.
Yeah. So first thing, keep yourself unmuted. I have another question for you. So the first thing to note is here every process is waiting for another process, right? Okay, I mean every process is waiting for a resource which is allocated to another process. So basically every process is waiting for another process. Now the question is, does the deadlock involve only P2 and P3 or does it involve all the three processes?
It involves all three, because if even P1 can give up its R2, then also P3 can proceed.
Exactly. So see this, okay, I think you can mute yourself. Good. So the R2 actually has two resource instances. Okay. So, I mean, you might think that only P2 and P3 are deadlocked, but see, P1 is interdependent here because suppose P1 gets done. So then P1, okay, no, wait, sorry. P1 cannot get done because P1 is also waiting for R1, right? So all the three processes actually are in a deadlock. You cannot say only P2 and P3 are in a deadlock, right? So actually all the three processes are in a state of deadlock. Okay. Any questions here? So now I hope you understand why we reverse the direction of the edges. Sure, there could have been many other ways to differentiate between a request edge and a allocation edge, but we specifically chose to reverse the directions so that we can detect such cycles. So any question here? If not, I have a question. Okay, Srihas is asking, is there an upper limit on the number of request edges for a process from a process? So Srihas, completely depends on the system. I mean, if the system is designed such that there is an upper limit on the number of requests a process can make, then yes. But there's no fixed answer to this. Of course, there is some upper limit. Say, for example, maybe you know that, say in Linux, uh, can you open as many files as you want? Can you open an infinite number of files? I don't think so. There should be some limit. Or maybe can a process create multiple, infinite number of threads? I doubt. There should be some limit. But for all practical instances, these limits are quite high. Usually never reach them, but yeah, there should be some limit. Okay, so since there are no other questions, let me ask a question. So we see here that a cycle indicates a deadlock, a cycle in this particular graph. But the question is, does every cycle in a resource allocation graph denote a deadlock? Okay, Soumitra, why not? If you want, you can unmute and say.
Sir, there are many instances of a resource in the graph. So, how much resource instances are there? Every instances should go through a common part of the cycle.
Right, good. Yeah, so basically I see that many of others also have given the same answer. So it kind of depends on how many resource instances are there. So actually let me show you a graph where there will be a cycle, but there will be no deadlock. And again, I want some of you to explain why is there no deadlock here. So specifically, what I want you to say is, how can the processes complete without getting into a deadlock? First of all, understand that there exists a cycle between P1 and P3. Like so P1, R1, P3, R2, P1, that's a cycle. But I am claiming that there is no deadlock in this graph. So tell me how. So how to prove that? A standard way of proving that is actually tell me a sequence of processes by which every process can execute, can complete. Okay. So yeah, maybe what? Okay. Yeah, I see some good answers. Fine. So basically, let me just summarize. Yes, so say P2 and P4, any of these may simply complete because they are not waiting for any other resource. The only resource that they want is allocated to them. Right, so say P2 completes. Right. So let's say, yeah, what Pankaj and Ramnivash said. So P2 completes. That means this instance of R1 will be free. So then this can be allocated to P1. Then P1 will get both the resources it wants, R1 and R2. So P1 can complete. Then P3 can complete and so on. Right? So every cycle in a resource allocation graph does not mean a deadlock. So basically, yeah, some of you have already guessed it, what Soumitra also said. So if a cycle is a necessary condition. So if a graph does not contain a cycle, then there is no deadlock. But if the graph contains a cycle, then there are two cases. One is if every resource type has only one instance, then a cycle also becomes a sufficient condition. So then there is a deadlock. But then if there are several instances per resource type, then there is a possibility of deadlock, but there is no guarantee, even if there is a cycle. Okay. So we have discussed two types of characterization of deadlocks. One is by those four conditions, and the other is a graphical way of representing deadlocks. So at this point, any question, then ask. Okay. Okay, Shubham has a brilliant question. That all this what we are discussing is at runtime. Can deadlocks be detected at compile time? Okay, so okay, Shubham, first of all, I cannot say that it cannot be detected because I don't know of all literature. Maybe some people have tried this and Maybe under some conditions it is possible. So I cannot directly say no. But then it's a very difficult thing to do because how many different processes will you check while compiling? So you have code for one process. Here P1, P2, P3, how many different processes will you check together? And how do you know which other process your process can get in like deadlock with? So that is difficult. But yes, if you say things like, say I have one particular code and I know that I will fork 5 instances of this code only. Then can there be a deadlock between these 5 processes? Maybe that kind of analysis may be possible. Okay. So yeah, I don't have a complete answer to your question. It would be very useful to be able to detect deadlocks during compile time. But yeah, I mean, I can understand the difficulties, the practical difficulties. But yeah, you can look up the literature to see if someone has tried that. Okay, Shoumitra is asking, how can we identify deadlock in the many instances case? I do not know of any easy way. Yeah, I do not know of any easy way. Okay, Pankaj is asking, in the several instances version, does the resource with multiple instances being a part of many cycles ensure deadlock? Again, Pankaj, it will definitely indicate possibility of a deadlock, but I cannot say that it ensures deadlock. Okay, yes, Soumitra, go on.
Sir, in the many instances case, suppose there is a cycle and one resource has many instances. So if we consider each instance at a time and and every time there is a cycle and all the cycles have a common age, so can it be told that there is a deadlock there?
Yeah, what you are saying sounds plausible because I mean, see, just because every instance is in a cycle may not indicate deadlock because the cycles can be completely disjoint. But what you are saying sounds plausible. Yes, every instance going through a cycle and then cycles have a common edge. It's plausible, but then I cannot right now say that this will definitely indicate a deadlock. Again, I mean, at least the books don't say anything like this, but I guess there have been research done. So feel free to look up the literature to see if there exists some. I can tell you that the books don't say anything like this. Not only this book, but in general, otherwise books also don't say anything like this. But if some research paper has been published which do indicate some such thing, I mean, please try to find it. If you can find it, then let me know. Let me know also that like so basically some graph theory researcher etc. could have done this kind of analysis. But then they need to give some provable guarantees that yes, this is a sufficient condition for a deadlock even in this case. Right. So
Sir?
yeah. Yes.
Sir, if we analysis means if we go through this means what I have said, suppose that every cycle have at least a common age. So can it be proved if not in the literature, or can we?
Sure. Of course, you can try to prove it. So
Okay.
if it is not in the literature, and if you have this idea, then sure, definitely you can try to prove it, and that would be a good work, right? So yeah, so some of you might take that as an exercise that try to prove it. But yeah, before doing that, I would seriously suggest that look up the literature. Okay, let's proceed. Okay, so now we will discuss actually ways of handling deadlocks. But before that, let me ask you a kind of a high level question. What do you think current operating systems do to handle deadlocks? Just very high level answers I want. What do you think they do? Okay, preemption of certain kind. Kill the process and restart. Any other answer? Okay, the actual answer will surprise you. Yeah, okay, Pankaj is also saying the same thing. Preempt the resource sharing. Yeah. Okay, Ramniva. Okay, what Ramniva says is correct. Multiple processor may mean more resource, but then again, we are not talking about only the processor as a resource. We are talking about input devices, output devices, and many things which you really cannot have multiple. So, I mean, sure, you can say that I build a fantastic system where every resource will have 5 instances, but then this is a bit like, I mean, fantastic, as in, yeah. The same thing with Tanmay is asking, sure. I mean, I might always say that I'll build a fantastic system where every resource will have 5 instances, but that's not practical because there is a huge cost involved, right? There's a huge cost involved also. So by the way, I think both in the networks course and this course, OS and networks, and in any systems course, understand that many of the decisions are taken based on the economic factor also, right? So it might seem, oh, this is a bad reason to give, but then it's the practical reason. So think in a network. I guess in the networks course, you are discussing things like if a network link fails, then an alternate routing strategy have to be found. Maybe you are discussing this kind of things in a network course, or maybe you will. So then why not say this, that, okay, replicate every link. Let's have 3 instances of every link in the network. Then you don't need such algorithms. But then what is the cost involved? Is it feasible? Often the answer is no. So in system courses, many decisions are taken based on economic factors or the cost involved. So if you remember, just going back to several weeks back, right at the beginning of this course, we were discussing about, what was that point we were discussing about? Yeah, I think we were discussing about that whenever a system call occurs, the kernel has to, save the process state, the kernel has to run frequently, and these things we were discussing. Someone, forgot who, asked a very interesting question. So if that is that big of a problem, why not have a separate set of registers for the kernel? Just a separate set of registers for the kernel, so the kernel doesn't have to use the same set of resources as the other processes. So the kernel can, the context switch overhead would be quite reduced. The kernel will use its own dedicated set of registers. That's a very good suggestion. But what is the cost? To have another set of registers in the same chip, right? That means you have to actually change the what is called, the design of the chip. That means the layout of the chip. What is the cost involved? It will possibly be 1.5 times. And then if you put out a processor in that market which costs 1.5 times, then people will say, what the hell? You have another set of registers and you are keeping it only for kernel. Who cares what the kernel does? I want my processors to run quicker. Right. So many of these decisions in systems are taken based on cost. Okay. So having a multiple processor, sure. Having many instances of a resource, sure. All these are great suggestions. But then what about the cost? Okay. So those are correct suggestions that you are giving, but they are not very practical. So the reason for my big introduction was I wanted you to prepare for this answer, because the actual answer is kind of surprising and many of you would be disappointed. Actually, a modern OS does nothing to prevent deadlocks. They simply let it be. Okay. Let me just go to the next slide. I will discuss all the things written at the top in black, but look at the point in the red at the bottom. That's one way of handling deadlocks. That don't try, just ignore the problem and pretend that deadlocks never occur. And this is what is done in most systems. Okay, so I know you are all disappointed. Why are you even studying this, etc. But okay, before going there, why do you think this is the case? Why do you think an advanced operating system like Unix will simply pretend that deadlocks never occur? Okay, Shubham has one feasible answer. They are very rare. Anything else? Okay, Srihash and Shomitra. Well, that's an idealistic. No, see, I can't agree to that. What you are telling. Who know? I mean, so many people are writing code. Like, who knows? Like, what kind of code people are writing? I mean, it's infeasible to assume that everyone will follow all different protocols and then write process code. Right? So that's not the idea. Okay. What Shubham said makes sense. They are very rare. Pankaj is saying there are generally multiple instances of resources. Okay. I mean, again, I don't fully agree, but feasible. Something else I'm looking for. Can any of you think of some other reason for which OSs decide to ignore deadlocks? Okay. So, okay, I see that, yeah, like the last answer by Tanma is going towards the solution, but let me say, okay, exactly what Sriharsh mentioned, that is what I was looking for. Think of the algorithm we just discussed. So the kernel will have to keep track of this resource allocation graph. So what does the kernel have to do? Every time it is allocated the CPU, it will have to update the resource allocation graph. For that, it will have to check which process is holding how many resources, which process has requested for how many resources. Based on that, it has to update the resource allocation graph. Then it has to detect a cycle. If so, then it has to choose which process to kill or which process to preempt. Too much of an overhead. And if the kernel actually tries to do this, then the chances of deadlock will even increase because now the kernel is holding many resources. Right. So the cost of detecting a deadlock is too much. They are not very common, as Shubham pointed out. The cost of detection is huge. So just pretend that they don't occur, just ignore them. If a deadlock does happen, the system designers have taken this decision based on human nature. If a deadlock does happen, some people will get impatient and will simply kill their code themselves. We often do that, right? The internet browser is not showing us a page for a long time. We simply restart it. It's human nature. We are impatient. We don't wait for so long. So the system designers thought that instead of trying to have a big algorithm running to detect deadlocks and then trying to handle them, just rely on human nature. If deadlocks are, first of all, deadlocks are uncommon. Second, if the deadlock happens, some users will get impatient and simply close their processes. Okay. Again, you might not like the answer, but then many decisions in systems are taken based on practical considerations, the cost involved, and so on. And I guess you will come across this repeatedly both in your networks course and this course. Right. So sorry to be disappointing you, but then actually nothing is done in modern OS to handle deadlocks. Yeah, but still, I mean, it's good to know about, it's useful to know about deadlocks. That's why we are devoting a couple of classes to this chapter. Yeah, so like wicked teachers like me often ask questions from deadlocks in grand vivas and all. So for all those reasons, it's necessary to know these things. That's why we are discussing this. Okay. Okay. So yeah, just let me just complete this slide and then we will stop today. Okay, Srihash is saying, what if there is a deadlock between kernel processes and user processes? Is it ignored even then? Okay. Okay, first of all, okay, good question, very good question. Okay, let me not try to answer it because some things are not clear to me. Does a kernel actually request for a resource which users are requesting for? A kernel will never request for a printer or a keyboard, something like that. Maybe there can, but say even semaphores. I can't imagine a kernel process requesting for the same semaphore that a user process has declared. Impossible. So I can't even think of a scenario, Srihash, that a kernel process is requesting for the same resource as a user process. I'm not saying it cannot happen, but from the top of my mind, I cannot think of such a situation where a kernel process and a a user process has got into a deadlock. Because I can't even think of the two requesting for the same resource. I think of a semaphore. A semaphore is created by a user process. How does the the kernel code should not even know of the semaphore maybe. Okay, not that. What I meant to say is the kernel process cannot have any conceivable reason to try to lock this semaphore. Think about it. I'm not saying that this can never happen, but from the top of my mind, I'm not able to think about a situation where this can happen. Okay. Okay, yeah, let me just complete this slide and then we'll stop. So basically, if okay, so how to prevent deadlocks or how to handle deadlocks? There are two broad ways. One is ensure that the system will never enter a deadlock state. Second is, okay, if there is a deadlock, then detect it and then resolve. Okay, so there are these two broad ways, and even among them, say this method of handling deadlocks that the system, ensure that the system will never enter a deadlock state. That again has two variations. One is deadlock prevention. So remember we discussed 4 necessary conditions for deadlocks. Just use a protocol to ensure that at least one of the necessary conditions do not hold. Then you can prevent deadlocks. So basically apply restrictions on how processes can request for resources. Okay, that's one way. Second way is the kernel analyzes the resource allocation state, maybe using a graph like that, to determine whether granting a resource request might lead to a deadlock later on. Right? So suppose a process has requested for a resource, the kernel does some analysis, maybe using the graph or maybe some other way, before granting this resource. Basically, it tries to understand that can granting this resource right now lead to a deadlock in future, a potential deadlock. If so, then it does not allocate that resource right now. The process is made to wait. But if it seems that safe, okay, then go ahead. Okay. And yeah, so that's one way that ensure that a deadlock never happens. Second way is if there is a deadlock, detect and resolve it. So yeah, the kernel analyzes the resource allocation state and then checks whether a deadlock exists. And if so, then it has to abort some processes. But again, the difficulties arise like which process to choose to abort. Whichever process you choose, it will be kind of unfair towards that process. So which one to choose and so on, right? So you see, we will discuss these things in the next lecture, but all these processes come with a lot of practical difficulties, which is why basically this is what is done. we ignore the problem and pretend that deadlocks never occur. Because detecting them is itself a costly operation. Even if you can detect them, taking states decisions like which process to abort, that's a big decision. I mean, ideally you don't not like to do that. Okay. Okay, we stop here today. Any questions? I have a small announcement to make. Okay, let me announce. Okay, so what I understand is next few days is spring break. Good, so enjoy the spring break. So the spring break is till when? Wednesday. Is it till Wednesday, 3rd March? Can just confirm, can you? Is the spring break to till Wednesday, 3rd March? Okay, so then the official next class would be on Thursday, 4th March, fine. But then I am yet to confirm. I may have a research related meeting on Friday, 5th March. So I may not be able to take the class on 5th March. If so, then I'll record the lecture. I'll record a lecture on 3rd March during the class hours. I'll confirm on Teams if I do so. If any of you want, you can join. It is always better if a few join just for interaction. But otherwise, I'll keep the lecture recorded. You can check it later. Okay. Fine. So officially, the next class will happen on 4th March, and the live class. But I might record a lecture on 3rd March during the class hours. I'll inform on Teams if I do so. Okay then. Thanks everyone. Let's end the class. So it was a good interactive class today. Thanks.